Swayam Prabha. Digital India. Educated India.
So let's continue our discussion on liners for landfill, and we are spending so many lectures on this because this is critical. You have liners which either work or which they don't work, and if they don't work, it's a big problem because you can't access the base to repair them. If you're living in a duplex house and your bathroom floor begins to leak, then you can always go to the top, break down the floor and get your water pipes and sewerage pipes to be redone. If you don't live in a duplex house, somebody else is living on top of you, he has no problems. But you are getting the wet patches in your roof because his pipes are leaking. But if you are in a landfill, nobody is living under the liner and nobody is living above it. So it's difficult to repair in such a situation. So let's spend some more lectures on this and get this right. So just a recap, we have been looking at the liners and we have talked about a composite barrier and we talked about single composite system. So this is where we left off last time, that if you have a municipal solid waste landfill, you'll have a waste, you'll have a filter separator, the leachate collection layer, a protector, geomembrane, compacted clay, a filter separator and subsoil. In a double composite liner, this subsoil will not exist. Again, the secondary system will repeat itself, and there you will definitely need this between the coarse grained soil and clay. Now, we had a very nice diagram here which shows a perfect geomembrane. Now you are putting a geomembrane on a football field, right? There will be defects. It will tear, it will have holes. You can be very, very careful about it. You will say nobody will walk on the geomembrane with shoes. How does that sound? So I said, okay, you can come with cloth shoes or tennis shoes, the old tennis shoes, lightweight, light soles. None of these hard, big boots that we wear. So there are stringent restrictions as to how do you lay these liners. They have to be welded, people have to walk on them. Therefore, all liners have punctures. And what it shows to us, our literature over the last 15-20 years from the developed world, is that when the quality of construction is very good, excellent, you will have 2 to 3 small holes per hectare. A hectare is 100 meters by 100 meters, like a football field. You will have 2 to 3 small. An excellent construction. All visual inspections, everything. However, most of the time the construction is poor. Then you have 30 to 50 small holes. Now that's a lot of holes, but they're all there. Somewhere the screwdriver fell down, somewhere a brick fell down, so it's all there. When you have, and what's the definition of a small hole is 100 millimeter square, so 10 millimeter by 10 millimeter is 1 centimeter by 1 centimeter. But a large hole is, what's a large hole? 100 millimeter square to a 10,000 millimeter. That is 100 mm by 100 mm. 100 mm by 100 mm is about 4 inches by 4 inches. So that's a tear. In the US, this is recognized, and they say if the amount of leachate coming in the secondary leachate collection system, that is the leak detection layer, is about 1,000 liters per hectare per day. How much is 1,000 liters? How many buckets in 1,000 liters? How much is your bucket? I think 15 to 20 liters. So how many buckets? If 50 buckets come, the alarm is on. That means your landfill is leaking and you have to take action. What is the action? We'll discuss later. And if it continues to leak and it becomes larger, you have to close the landfill. If it becomes anything above 10,000 liters per hectare, before that you don't take action. Some leachate will always come in the secondary layer. Why? Because some holes will always be there. And if some holes are always be there, something will come out. But that's design. And that our secondary leachate system will take care of. Okay? So this is American practice. And in India, whenever I go and talk to somebody who's got a double liner system and say, can you share data with me regarding what is the amount of leachate which comes out in your leak detection layer? Sir, kuch nahi aata. Sir, nothing comes. So at least the Americans allow you to recognize that something comes, and I'm not going to call that the landfill is leaking. What are they worried about? The moment they report something in the secondary leachate collection layer, they will say liner is not working. Close the landfill, close the landfill. So there is always an issue of this. Remember, compacted clay is also compacted at OMC or higher. When you put the waste over it, it also squeezes and gives out its own water. So there are liquids which are coming out of it. So we've done this. Let's look at a composite liner being laid at one place. This is the landfill at in Himachal. You always get the kind of land that is available, and you have to do a lot of earthwork for you to understand. Look at, this is the landform. So all this earthwork you have to cut and fill, and you are creating one phase for 1 year. And here you are, I talk to you that if you don't have clay, then you have to mix with bentonite so that you can reduce the permeability. So here the soil did not have 10 to the power of -7 centimeters per second, and bentonite is available to us like cement, because a lot of people make drilling fluid. Metro is using a lot of drilling fluid for tunneling, for making boreholes, for piling. So drilling, so commercial bentonite is available. You can go to a shop and say, "Mujhe ek bag bentonite de do." It will cost you similar to cement, maybe half the cost or something. But so here you have spread the bentonite on the soil, and you are doing what is called in-place mixing. You are using a tractor with plows and harrows. Something like this, a claw at the back. This is not the prescribed method for doing this, please. In India we are doing it because it's the cheapest method. But you are mixing bentonite with the local soil, then you will sprinkle water on it, and then you will compact it. But this is called in-place mixing to make the soil impervious, and we are now compacting it. This is not the roller you should be using. What type of rollers do you use in clays? Oh, great, wonderful. So sheep's foot rollers are the ones which have to be used, not road rollers or smooth steel drum rollers. And I will come to that why. Now you rolled it and you made a sump here, but can you get a feeling that this is an inclined floor? Well, that is exaggerated because I took the photograph by standing a little more inclined. Actually, it's almost horizontal. But I took it such that you would feel it's inclined, because it is actually inclined in two directions. You have a slope in this direction also and a slope in this direction, and all the water will come here. And that's your geomembranes coming in a truck in the form of rolls. And remember my story about, not a story, a fact about the size of the space shuttle and the backside of a horse. But that's because it came by a rail track. These are the rolls. Now you see the way it's being handled. Will you not have cuts? The geomembrane on the side slope, and it is being anchored in an anchor trench at the top, and the roll has limited width. It's got to be welded together. So here is the welding going on, and people are sitting on it and working on it. He's not wearing the tennis shoes which I asked. And this is a HDP. When you heat it, it melts. It becomes soft. So you can just do thermal welding. Okay. And there was he's doing patch welding here. There was a tear, so a patch is being applied. I want you to remember this. I'll come back to this shot. This is a foot pump, so he's pumping in air in the joint. Now how he's pumping in air in the joint will come to later. There's a peculiar way this joint is made. But I can tell you whether 20 meters of this length is leaking or not. So I make a joint. It has to be a leak-proof joint. And in geoenvironmental engineering or environmental geotechnics, this is the most critical part. The geomembrane is fine. The joint should not leak. So we have to ensure, it's like saying when you weld two steel sheets, the steel joint should not leak. We have to do that. So now on the geomembrane, we are putting a protector, and I'm stitching this. This is non-woven geotextile. Let me see if I can show this to you on this projector. This is a geomembrane. The geomembrane is nothing but a solid, thick plastic sheet, and it can be smooth or it can be rough. Can you see this? It just looks like a square, a rectangular piece, but it's smooth. And if I put this in the light is shining off it. Can you see it? This is a smooth HDP geomembrane. It's pretty thick. You try and bend it, and it doesn't bend so easily. It's not like the thin panni that you have, which is used for making your plastic bags, or a vegetable vendor will have on top. This will not bend so easily. This is a smooth HDP geomembrane, 1.5. This is a textured geomembrane. Well, the texture doesn't come out so well here, but if I now do the same thing as I did, can you see the roughness? There is a roughness on the surface, and if you feel it, it will be like a sandpaper. So this is a textured geomembrane. And also you are seeing something white. As I told you, it's like a blanket. That's a non-woven geotextile. You can see thin strands. If I just try and you can pull out the strands of filaments from this, okay? But it's like a spongy, blankety material. So these are used in the landfill. This is a lightweight material. What you use in the field is thicker than this. That's why I use something called, a term called 400 GSM. That was 400 grams per square meter. So here also now, if I come back to what we were watching earlier, that you will see that we have, that's the geomembrane, that's the joint, that's the non-woven geotextile being placed over the geomembrane to protect it as a protector. And geomembrane, and you can see people walking over it. Of course, he is barefooted, and you can see this white protector, and on top of it you can see the leachate collection layer. And this looks like sand or more? This looks like gravel. Does it look angular or can't make out? Well, the river, there's a river nearby, so it's rounded. So now you can see the cell is complete and it is ready to receive the waste. So make an impervious thick base, put a geomembrane on it which comes out in the form of rolls, and then make the other elements. So for clay we have the following options. because we need 1 meter thick clay. If you have in situ clay, it's very good because you can excavate it and recompact it at optimum moisture content or more so that you can get the required permeability. Or you may also import clay from nearby areas. So clay should be available between 20 to 50 kilometers. In Delhi, you won't get clay between 20 to 50 kilometers. We are sitting on the Indo-Gangetic plain and mostly it is sandy silt and silty sand. Then you do what is called an amended soil. An amended soil is take the soil which is available to you and add 5 to 15% bentonite to it, commercial clay. Kaolinoid is not that easily available, it is not that effective, but you can add 5 to 15% bentonite, and that sometimes brings your permeability below 10 to the power of minus 9 meters per second or less than 10 to the power of minus 7 meters per second. Or you may have to import clay from far off area. Right? Now, if you are lucky, this is just a base figure, don't treat it as rupees per cubic meter, this is with a base value of 100. So if your in situ clay is available, you have to recompact it. This may be the order of magnitude. If you are getting it from 20 to 50 kilometers, this may be the order of magnitude. In amending the soil, the main issue is mixing the additive to the soil. Amended soil is soil stabilization with additives. This is what it will cost. If you have to get imported clay from far off, it will cost you this much. So the main thing is identifying the borrow area, performing the laboratory tests to confirm the permeability, and then to construct. So the requirements, let's not forget, we need permeability less than 10 to the power of minus 9 meters per second or 10 to the power of minus 7 centimeters per second. Thickness should be about 1 meter. Now within this 1 meter, can you compact, you've done compaction of clay? What is the layer thickness that you use for compacting sand and for compacting clay? Firstly, what is the type of roller that you use for compacting sand and compacting clay? What roller do you use for compacting sand, clean sand? So vibratory, smooth steel drum roller. Just don't use the word vibratory in isolation, because you can have a vibratory sheepsfoot roller, you can have a vibratory padfoot roller, you can have a different kind of roller. So you use a vibratory smooth steel drum roller for compaction. For clays, you use a sheepsfoot roller. Vibrations have no effect. The main issue is what kind of thicknesses do you use for soil compaction? What is the layer thickness? Well, in sands you can use relatively thick layers. If you're using a vibratory roller, you can probably use even 60 centimeters thick, 45 to 60. But in clays you can't. So you typically are dealing with lower thicknesses. So at least 3 to 4 layers of compacted clay, each 0.2 to 0.25 meters thick, properly bonded. Properly bonded means there should be fusion between the old layer and the new layer. And when you compact with a sheepsfoot roller, the top layer is not smooth. When you compact with a smooth steel drum roller, then the layer is smooth. You remember doing your Proctor compaction test? You compact one layer, then you do scarifying with your spatula. Why? You want the next layer to be bonded. So when you use sheepsfoot roller, the sheepsfoot will create these pock marks. So you don't have to do any scarifying. Okay? So they are properly bonded. The main issue is you should have no lumps or clods. When you excavate clay, it is plastic. When it's plastic, you get clod size. And if you use a smooth steel drum roller, it is not going to break up that clod, especially if you are using a thick layer. So by using 8 inches of layer and using sheepsfoot roller, you are breaking up the clods. And therefore, after that, you can do the compaction properly. There should be no shrinkage or desiccation cracks, which means as soon as you compact, please cover with the geomembrane. If you compact today and leave it exposed, and if it is a high plasticity clay or if it is a clay which shows shrinkage, then the cracks will form. So critical is compact and cover. And we will look at this influence of leachate, etc. Just in a few minutes. So a lot of things are written on this slide. But what it says is permeability is low when percentage of silt plus clay is high, when percentage of clay is high, gravel is absent, but don't copy this, this is going to be available to you on your Moodle. Plasticity index is high, void ratio is low, compactive effort is high and of kneading type and done wet of optimum, clods are absent and no shrinkage cracks. Then you get a good compacted clay liner. Sands and silts have permeability much higher than 10 to the power of minus 9 meters per second, but clays and silty clays have permeability less than 10 to the power of minus 9. So this is fine. Sands and silts when mixed with 5 to 15% of bentonite will have permeability less than 10 to the power of minus 7 centimeters per second or 10 to the power of minus 9 meters per second. Most contaminants in the leachate in the normal range do not significantly affect permeability. We'll look at this, we'll look at the data on this. But there will be some contaminants which will affect, but most contaminants will not affect it. So remember, we go back to our standard compaction procedures. We go back to our standard compaction procedures. And this is the light Proctor compaction test, this is the heavy Proctor compaction test. If you are compacting dry of optimum, you are going to get a flocculated structure, we all know this. If you are compacting wet of optimum, you are going to get a dispersed structure. When you have a dispersed structure, your permeability is low. So we prefer to compact wet of optimum because vertical permeability is lower than the flocculated structure. So that's an important thing that you should remember. And this is a lot of data which I compiled from various sources, and if you are looking at this horizontal axis, as the gravel content increases, permeability increases. As clay content increases, permeability increases. The shaded portion is the data from all across the world. As plasticity increases, permeability decreases. And remember, you have to be below this. Void ratio increases, permeability increases. Degree of saturation, saturated clay will have more permeability than unsaturated. If you do a permeability test wrong, you wanted to do a test on a saturated soil, but you are actually doing it, the saturation was not complete, you will be underreporting the permeability. Static compaction, dynamic compaction, kneading compaction. Kneading compaction gives you least permeability. Higher compactive effort, low compactive effort. As the compactive effort increases, permeability goes down. At OMC, minus OMC, plus OMC. On the wet side, you have lower permeability. If you have cracking, you'll have high permeability. And if you have clods, that means if you have not broken down the clods, then the permeability will be high, because flow will take place between the clods. Have a look at this. These are the clods. If you don't break it down, the clods effectively function like a coarse-grained material. And here, once the clods are broken down, the circuit is more tortuous and permeability is lower. And then the question that we asked, how do chemicals affect the permeability of clay? So this is K with the leachate as a function of K with water. Okay? So if you are higher, that means with leachate your permeability is higher, so it's not good. If you are lower, it's fine. So with acids, if you see, permeability of clays is not much affected. It's only 10 times what it was earlier. With alkalis, it may not even go beyond the original value. This is the original value of water, 10 to the power of minus 7 centimeters per second. With inorganic cations, that means you have calcium and others, calcium chloride, sodium chloride, this may go up a little. Concentrated salt solutions, it may go up a little. So 10 to the power of minus 7 may become 10 to the power of minus 6, and this is built into the recommendation that your permeability should be less than 10 to the power of minus 7. That even if all this happens, it won't go beyond 10 to the power of minus 6. However, there is one area that you see here It's called organic solvents. And here it goes up to 100 times or 10,000 times or more. And why does this occur? And this is the most critical aspect that you have to understand. Okay? Permeability in clay is determined by what? Why is it that high plasticity clay gives us low permeability? If I have sand and clay both at the same void ratio, which will have more permeability? Same void ratio. If I have sand and clay both at the same void ratio, which will have higher permeability, and why? E is 0.5. Why will sand have more permeability? And why so much more? The void space? Because of the structure? Because of the size of the voids? Okay. One has less number of bigger voids and the other has more number of smaller voids. All of them have the same airspace because the void ratio is the same. Volume of voids divided by volume of solids. In both the soils, airspace is the same. And why should it make such a difference? What is the permeability of sand? Typically, let me say, even if it's fine to medium sand and clay. So why should there be a 10,000 time change in permeability just because the soils are finer? If I take the sand and I crush it and 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 bring it into the silt clay range, will the permeability become 10 to the power of minus 7? It won't. It just won't become that. Because though you have finer particles, though you have finer voids, still the permeability will not change by this much, a million times. And what is the main difference between the two? Sand is inert and clay is electro. Yeah. So first is sand is round or subangular or angular, may not be round. Clay is plate-like or needle-like. But more important is that clay has large area which is negatively charged. So here you have sand particle, here you have another sand particle, here you have clay particle, here you have another clay particle. Right? The difference is this is neutral, this has a net negative charge. When water flows through this, two voids, the similar void ratio, the same size, water will flow like that. When water flows through this, what will happen? So for some of the water will get attracted to the clay layer, so it will get attracted to the clay layer and a double layer will form. So the water will flow through this. The higher the plasticity, the bigger the double layer. The higher the plasticity, the bigger the double layer. In bentonite, so the double layer is the held water. The double layer is the held water, therefore the space for the free water is very limited. So this is smaller space and this hardly has any space. So the more plastic the clay, for the same void ratio, the permeability goes down. It has little to do with the void space, it is the size of the double layer. So when will a double layer become smaller? Now that's the critical question. I send calcium chloride solution through the water. What will happen to the double layer? It will increase or decrease? He says increase, you say decrease. Tell me why it will decrease and why it will increase.
Because the negatively charged particle will attract the part of it and it will increase the.
So calcium is Ca2+, right? And water is electrically neutral. So calcium will go to the clay. It will be attracted to the clay. Once it gets attracted to the clay and it is 2+, a relative less amount of calcium can remove the effect of the negative charge. So when you send in a concentrated salt solution, the double layer will decrease because the 2+ ions will come and sit here, and for the same bentonite, which are these huge double layers, if I put the 2+ ions here, this will become this much. So first the calcium will go and sit on the clay, the void space for free water will increase and the permeability will go up. And that's why you saw in this diagram that when I have inorganic cations or concentrated salt solutions, everything goes above 1. But what happens when I have organic solvents? Organic solvents are non-polar. Water is electrically neutral, but polar. So a double layer is formed. If there is no water, then you have a non-polar. If there is non-polar fluid which is flowing, pure non-polar fluid, what will happen? There is no double layer. The net negative charge may exist, but the fluid is non-polar, it will flow like water. So that's why non-polar fluid can make the permeability go up a million times. But luckily for us, there is no pure non-polar fluid which flows through as leachate. Always there will be some water film, always there will be some water, no non-polar fluid. But if you are having a storage tank of non-polar fluid, then what will happen? An organic non-polar fluid. And if the storage tank is leaking, then eventually only non-polar fluid will be flowing through the void space and then the permeability will become very large. So that's the problem with bentonite, that it is badly affected by non-polar fluids. So I just want to give you this so that you remember. I'm talking of meters per second at E equal to 0.5. Clean sand, silts and silty sands, we want 10 to the power of minus 9. Silty clay, low plasticity clay, clay of medium to high plasticity, bentonite, commercial bentonite, 10 to the power of minus 9 to 10 to the power of minus 11. Please see here. But commercial bentonite is the one which will be most affected by polar fluid, because the more the net negative charge, the bigger the double layer and the more the effect. So I would not use, for the purpose of my liner, a high plasticity clay or only commercial bentonite, because it is extremely highly affected by polar fluids, right? I would like to use low plasticity material. If it is low plasticity, it is not that affected. It's like your crushed sand. It's like your crushed sand. And if I have sand and silt and clay mixtures, see, bentonite will also show high shrinkage cracks. Bentonite clays are swelling and shrinkage. So you have issues of desiccation cracks, a lot of cracking if it dries up by mistake. So we like to make our liners with sand, silt, clay mixtures. That means you mix the silty sand in Delhi. If you mix the silty sand with commercial bentonite or some commercially available clay, in Delhi Dhanori clay is available, then I can get 10 to the power of minus 9. That's what I want. It will show no shrinkage, no clods, because the plasticity index is not very high. But the fine particles of the clay have sat inside the void space and it is reducing the path of flow. So just for our discussion, commercial and bentonite clay, this is in centimeters per second, both of these. Do remember that we are now 10 to the power of minus 9 to 11 and 10 to the minus 13 centimeters. That makes it 10 to the power of minus 11 to 10 to the power of minus 13 for meters per second and 10 to the power of minus 15 meters per second for the geomembrane. Eventually, we have to perform these laboratory tests on clay, and we have to use some laboratory testing devices for finding the permeability of clay, because we have to assure this 10 to the power of minus 7 centimeters per second, and these are not your standard falling head permeameters or constant head permeameters. We'll do this in the next class, and we have to then work out how do I get the coefficient of permeability below the acceptable level. So we have to do this Proctor test and the modified Proctor test and get these permeabilities. And we have to compact wet of optimum, as I told you last time. And here you will be able to find out through your laboratory what is the additive content that you need. For example, in Delhi silt we are adding bentonite clay, and you see about 5% clay is sufficient for getting the permeability that we need. So we'll do this laboratory testing in a little more detail in the next class. But what we found out is it's a very, very careful, quality control condition construction that gives you the good liner. If you mess up on any of the things, not good quality clay, if you mess up, don't compact it properly, you don't mix it properly, you don't use the correct rollers, you can have a difference in the permeability of your material. So it's a high precision construction quality control job. So with this we end this today, and in the next class we'll take up the permeability testing of clays. Thank you.